In the previous video, we got a first glimpse at the Peripheral Management Unit, a peripheral block unique to Maxim microcontrollers that's a little like a DMA unit that's been working out and has started to think it's a CPU core. Well, like a CPU core, the PMU fetches and processes opcodes, but the PMU has 6 opcode processors, so it can execute 6 separate operational sequences at once. The PMU has an instruction set just like a CPU, except in the PMU, we call the instructions descriptors. Each opcode processor fetches descriptors from memory just like a CPU core and executes the descriptors to perform data moves, rudimentary logical and arithmetic operations, and conditional and unconditional jumps. The opcode processors have unlimited access to both the AHB and the APB spaces just like the main CPU core, but the PMU isn't really a CPU, it's much simpler, with only 8 descriptor types. When you look at the descriptors, you'll see they're pretty inefficient when it comes to instruction coding. That's intentional. The descriptors are made to be simple and universal, easy to understand and build by hand. Programs for the PMU may be as short as 1 descriptor or as long as several dozen, but usually it's just a few descriptors. There is no stack, no push and pop, and no subroutines. Generally, a PMU descriptor list starts at the beginning and ends at the end, with perhaps a few pauses along the way. The heart of the PMU is a round-robin scheduler. It gives every PMU opcode processor a fair shot at accessing the bus, whether to fetch an opcode or whether it's moving actual payload data. Each opcode processor can be in one of 4 states: disabled, enabled and waiting for a descriptor, enabled and executing a descriptor, or enabled but waiting for an event to occur. Setting up the PMU is really easy. There are only 3 registers that need to be configured for each PMU channel, and chances are you'll only need 1 channel. The first register contains the address of the list of descriptors for this PMU channel. Now, you can put the descriptor list anywhere in memory. You can build it in RAM if you want to, or just declare the descriptors in the list as constants in Flash. It really doesn't matter. Just like a CPU core, the opcode processors will fetch the descriptors one at a time from sequential addresses until they hit a jump or a stop. The second register configures the channel options for the opcode processor and provides status to the CPU. Bit 0 enables the channel. It's the last bit you'll set before you put the core to sleep. When the core awakes again, it will inspect bits 2, 4, and 6 to see why it was awakened. Bit 2 means it was awakened because the opcode processor executed a normal stop. Bit 4 means that the opcode processor encountered a bus error, and bit 6 means that the operation timed out in the opcode processor. Now, speaking of timeouts, the TO cell field, the timeout select field, determines how long it takes before the channel gives up when waiting for a signal or when polling a memory address. The timeout value is given in units called PS intervals, and the duration of 1 PS interval is given in the PS cell, the PS select field, and we'll get to that shortly. TO cell is a 3-bit field, and the timeout value is exponential. A value of 0 in this field provides a timeout value of 4 PS intervals. A value of 1 provides a timeout of 8 PS intervals, while a value of 7 provides a timeout of 512 PS intervals. The very next field, PS cell, chooses how many PMU clock cycles comprise 1 PS interval. Now, your choices here are pretty coarse: 2 to the 8, 2 to the 16, or 2 to the 24 PMU clocks. And remember, this only affects the timeout. The actual PMU state machine operates with the same clock that the CPU core uses. Bit 16 is the interrupt bit. It's set when the opcode processor completes an opcode that has its interrupt flag set. Bit 17 is the interrupt enable bit. It allows the interrupt bit in bit 16 to assert an interrupt toward the ARM core. If this bit is clear, the interrupt bit may become set, but it won't actually interrupt the core. And finally, the 5 bits at 28 down to 24 contain the burst size. That's the maximum number of bytes that this opcode processor channel will attempt to transfer in any one transaction. That doesn't mean you can't transfer more. It just means that after this number of bytes, the opcode processor will relinquish the bus and will allow the round-robin scheduler to move on to the next channel. Now finally, the third register is the loop register, and it contains two 16-bit fields. The two fields are actually two independent values that initialize the two counters in the opcode processor. These counters are used whenever the loop descriptor is encountered. And that's it. Each PMU channel consists of just 3 registers to configure. You point the channel at the list of descriptors, set the initial values of the loop counters, and write the channel configuration. And that's it. Now, in the next installment of this video series, we'll take a look at the descriptors themselves. See you then!